we can say that F is a band limited. The characteristic function on set E is denoted by chi E of xi. In 1984, Morlet introduced a first wavelet transform that is defined as follows. Let psi belongs to L2K be a mother wavelet. Then the continuous wavelet transform is defined as follows by this equation 3.1, which is said to be a wavelet transform. When psi belongs to the L1 intersection L2, then the admissible condition given by C of psi and the non-inversion formula is stated by this equation, equation 3.2. The aim of this paper is for band limited function. We will give another kind of inversion function of wavelet transform on local field. So next is preliminaries. So in preliminaries we state this theorem. Let psi of t belongs to intersection L1 intersection L2 and another function phi of t also belongs to L1 intersection L2 satisfying the pi cap omega equals to this. Then for any f belongs to L1 intersection L2 and the support of fk is a subset of closed interval minus omega to plus omega, then the following inversion formula holds. This equation 4.1 where h of t satisfy this condition and the above inequality holds in L2 sense. The limit in 4.1 is simpler than that in the equation 3.2 which we have seen in the above definition, and the function pi of t in 4.1 can be chosen freely. So before proving this theorem, we state this lemma. Let psi of t, pi of t and f of t be stated in theorem. Then for any g belongs to L2k, the following formula, this formula holds. So proof of this lemma as follows. By using Parseval identity of Fourier transform, we have this equation for the wavelet. Using the convolution formula and the Parseval equality, we also obtain this equation. Now again, applying the inversion formula of Fourier transform, it follows from equation 4.3 and 4.4. We get these two equation 4.5 and 4.6. Finally again using the Parseval inequality, we get this equation. Since support of fk is a subset under this interval, which is given by the support of h cap omega, where h cap omega is given by this. We know that f cap omega and the h cap omega is equals to mod omega f cap omega, where this omega also belongs to our local field k. Further, with this expression and this equation, and in the view of equation 4.5 and 4.6, we will get this equation. I mean, if this integration will be less than equal to norm of this pi psi f g. By Fubini theorem, we have this integration. Again, noticing that the mod omega integration over k is equals to inner product of pi cap and psi cap, which is equals to inner product of pi and psi. For repeated integral, we get this integration is equals to this. In order to complete the proof of lemma by Fubini theorem, we only need to prove that this h is strictly less than infinity. So we will split this h into two parts, namely h1 and h2. First we will show that this h1 is strictly less than infinity and then h2. Then we will finally obtain this equation 4.7. So first we'll see for h1. So by using the Cauchy's inequality, we get this h1 square into product of two integration, which is denoted by h11 and h12. Applying equation 4.5 and the Parseval identity, we have h11 as follows. By psi belongs to L1k, we know that there exists a absolute constant term m which is greater than 0 such that mod of psi cap omega is less than or equal to m. So h11 will be less than or equal to this On the other hand, applying the equation 4.6 and the Parseval identity, we also have H11 by this equation. Again, by pi belongs to L1k, we know that there is another constant term n which is greater than 0. So H12 will be also strictly less than this expression. So from these two, we can say that the 1 is strictly less than infinity. Similarly, we will repeat this similar process for H2. We will split H2 square into H2 to 1 and H2 to, and we will show that H2 to 1 and H2 to is less than equals to infinity. So from here, similarly, argument of equation this, we have H2 is by this integral. Further, by the definition of H of t, H2 can be written in this form. So from pi of d is equal to this, we have norm of pi is strictly less than m. Again, m is a constant term. So from here, our H22 is also less than equals to this. So our H2 is strictly less than equals to infinity. So finally, we have obtained the equation 4.7, where it was given that the H should be strictly less than infinity. So here the proof of lemma is complete. Our next result is followed by the proof of our theorem that we stated in the preliminary portion. So from this equation and the equation 4.10, we have this equation 4.5. So for all t belongs to k, we know that this w psi f p belongs to this space L1, and we consider a set del at from our theorem by this equation. So by the well-known result of the Hilbert space, we know that the norm f of t minus del t is equals to supremum of this. Again, by equation 4.2, we get this equation for del a g, and here we will be interchanging these two integration, and the reason for interchanging the order of above integration is stated as follows. So by equation 4.10 and by this integration, we get another result for this integration. So from this integration, it shows that the order of integrals in 5.3 can be interchanged. Now using the lemma and the equation 5.3, we get this equation. So further we get from equation 5.2, that is norm of fg minus del aj is less than or equal to supremum. So where aij we are denoting this expression. Now using Cauchy's inequality, we get to see that I square, which is less than or equal to this integration, can be written as the product of these two integrals, that is I1 and I2. Now imitating the estimate of H21 and H2, which we have seen in lemma, we get I1a by this and the I2a by this. From this and equation 5.4 and 5.5, we know that the norm of f of t minus del at is less than or equal to supremum, and when you take the limit of this norm, we get the 0. So here our proof is complete, and here are the some of the references which I have prepared. Thank you.
Thank you so much, Professor, for your nice presentation. And again, the next paper also belongs to your team, I believe. So who is
Yes.
going to present?
Sir, it's Kedjing Mongam. I'm going to
Oh,
present.
okay, Professor. Yes, you may continue, Professor.
Good morning, everyone. Myself, Kejim Wongkang, a scholar from Department of Mathematics, Nearest, Arunachal Pradesh. So, the title of my topic is Inversion Formula for the Wavelet Transform on Abelian Group. Previously, my colleague did it for local field. I'm doing it for Abelian Group. And the outline is like this. The abstract is, in this paper, a reconstruction and inversion formula of the continuous wavelet transform on abelian group for band limited function is defined. This formula poses a more explicit expression than the well-known result, and also Parseval and other interesting results on abelian group are obtained. So next is introduction. In 1984, Jean Morlet first introduced wavelet transform that is defined as an equation 1, where our W psi of f is the wavelet transform of the function f in L to G. And the no inversion formula is stated as in 2, where our C size is the admissibility condition, and this equation holds in L2 signs. And some definition, this definition of Fourier transform and inverse Fourier transform. The Fourier transform of f is denoted by f cap, and it is defined like this, and the inverse Fourier transform is defined like this, and the Fourier transform holds these properties, and we can say that our function f is band limited if the support of f cap is a bounded set. So to prove our result, we need this lemma. So this is in our preliminary. Lemma is let psi f and phi belongs to L1 intersection L2 G, where our f is a band limited function, so, and phi cap omega satisfy this equation. Then for any G belong to L to G, this formula holds. Okay, we'll prove this lemma. The proof is by Parseval identity of Fourier transform, we have this equation 4, and using convolution formula and Parseval equality, and from equation 3, we obtain this equation 5, and applying the inversion formula of Fourier transform, and from 4 and 5, we get these two equations, 6 and 7. And finally, again using Parseval equality, we get the below equation. And since our support of f cap belong to this closed interval, and which is equal to support of h cap omega, and this h cap omega equal to modulus of omega, product of characteristic of this set, we know that this equality holds. Further from this equation, and in view of this inequality, and by Fibonacci theorem, we have this equation. And again, by noticing this equation, and for repeated integral, we get this below equation. And in order to complete the proof of lemma by Fibonacci theorem, we only need to prove that this integral is denoted by k is finite, and we split this integral into two parts, k equal to k1 plus k2. Okay, k1 is okay. And first we'll estimate k1. By using Cauchy inequality, we get k1 squared is less than equal to the product of these two integral. The first integral is k11, second integral is k12. And applying 6 and Parseval identity, we have this equation. And by psi belong to L1G, we know that there is a m greater than 0 such that this inequality holds. So k1 is less than equal to 4 pi m squared norm 2f squared. On the other hand, applying 7 and Parseval identity, we have this equation 10. So by phi belong to L1G, we know that there is n greater than 0 such that this inequality hold. And again, noticing that for this inequality, we have this k12 less than equal to this quantity. So our k1 is finite. Next, we will show that k2 is also finite. We'll estimate k2 from 9, and we know that for any given epsilon greater than 0 less than 1 by 2, k2 is this one, this integral. And by using Cauchy inequality, we get k2 square is less than equal to product of these two integral, denoted by k21 and k22. Since from these two inequality, we get this inequality, So similar to the argument of 10, we have k22 equal to this integral, and further by the definition of hx, k22 equal to this integral. So from this value of phi cap omega, we have this inequality. Our m1 is a constant, so our k22 is less than this quantity. Therefore, our k2 is also finite. So we proved the lemma. Next is our result. So that is a theorem. So we stated this psi, phi, and f as in lemma. Then for any f belong to L1 intersection L2G, and this inversion formula holds where hx satisfy this equation, and the above equality holds in L2 sense. So this limit process in this theorem, this equation 12, is simpler than the well-known result, and the function phi f in this equation 12 can be chosen freely. So proof of the theorem is, so from this inequality, we have this equation number 13. So for all x belongs to z, we know that this transform of Wavelet transform of this function belongs to L1, and we set this integral equal to delta h of x, and by the known result in theory of Hilbert space, we know this equation 14. Again by 3, we get this equation 15. So by interchanging order of integration, and as follows, and by 11 and this inequality, we get this inequality. So the order of integral in 15 can be interchanged, and using lemma in 15, we get this equation, and further from 14, we get equation 16, where our I is this integral, and using Cauchy inequality, we can see this equation number 17. And imitating the estimate of k21 and k22 in lemma, we can get this I1 and I2. From this 16 and 17, we know that this norm of this quantities, this is less than equal to this quantity, and if we take the limit, then this norms is equal to 0, then means our this two functions are equal, then we get the theorem. These are the references. Thank you.
Thank you, Professor. Thank you. Nice presentation. And any questions from audience side, please raise your questions. Okay, Professor. No questions from the audience side, it seems. Thank you.
you,
Thank
sir.
you for your nice presentation. Thank you. Next, I'd like to call Professor Thamrai Selvi Bhaskaran and Rajasekaran Ganapati.
Good morning, sir. Thamrai Bhaskaran, I'm present, sir.
Yes, ma'am. Yes, ma'am. You may proceed, ma'am. Thank you.
Yeah, okay. Thank you, sir. Excuse me, sir. Share option.
Yes, madam. You are able to share. You check.
Yeah, sir. No, sir. It's not visible, sir.
Okay, I don't know what's
Share
happening there. Professor, they are not able to present their presentation. What to do, Professor?
Sir, my present option is not, it's a hide, sir. Sharing, it's a hide, sir. Sharing option is a hide, sir.
Okay, no one is responding, ma'am. Ma'am, you may wait. Maybe after the next one, I try once again.
Okay.
Maybe in between, I'll discuss with them. Maybe the next presentation you may do, ma'am.
Okay, sir. Wait.
Fine. So next, I'd like to call Professor Sushil Kumar Chaudhary and R.S. Jordan and Padam Singh. If you are here, Professors, please, you may present your presentation now. Professor Sushil Kumar Chaudhary, R.S. Jordan, and Professor Padam Singh, are you here? If you are here, means please
Padam
speak
Singh,
up.
sir.
Yes,
Padam Singh, sir.
yes.
Padam Singh, sir. Are you listening? Hello, Padam, sir.
No, sir, they are not listening. And Professor Professor Tamari Selvi told me that they are not able to share their screen. What's the reason, Professor?
But I don't know.
It's hidden. She told.
Padam, sir.
Hello. Yes, Sushil Chaudhary is not available right now. I think he will present
Yes,
in
yes,
another
they are
session.
able to share, Professor. They are sharing. No issues.
Okay.
Wait a minute, Professor.
Excuse me,
Yes,
sir.
ma'am.
Sir, visible, sir?
Visible, but your screen is not showing anything, ma'am. Some empty screen only. Maybe you try once again. Professor Tamari Selvi, madam, are you trying to share your screen once again?
Yes. Yes.
Please do
Wait,
it
sir.
as quick as possible because almost the time is over. We are having 3 more or 4 more presentations. Please do it as quick
Yeah,
as
sir.
possible. Again, it's showing some empty screen only, ma'am.
Actually, ma'am, please click on the entire screen.
Yeah, sir.
Click your entire screen.
I already opened, sir, but why it's show? I don't know that. Okay, sir, you can continue other person, sir. I will
Okay, ma'am.
try.
Okay, thanks.
Sorry, sir.
So next, I like to call Professor Ravikant Divakar and Professor Anil Kumar. If you are here, means please start your presentation process.
Yes, sir. I'm audible.
Yes, audible, Professor.
जी सर. सर प्रेजेंटेशन दिख रही है?
Yes, it's showing. No issues. You continue,
Yes, sir.
Professor.
Thank you, sir. Thank you. Myself, Ravikant Divakar, Department of Physics, Hindu College, Muradabad, a research scholar. My research work is under Dr. Anil Kumar, Associate Professor. My research topic is structure study of green synthesized zinc oxide nanoparticle using Wavelet Transform. This is abstract. Plants are good replacement of hazardous chemical used as capping agent for synthesizing the nanoparticle. Green synthesis of zinc oxide nanoparticle is performed using aloe vera gel as capping agent and obtained nanoparticle are calcined at 400 degrees Celsius. The XRD pattern of prepared zinc oxide nanoparticle is obtained and denoted using Haar wavelet transform. The sharp peak of XRD pattern indicate crystalline nature of zinc oxide nanoparticle. The interplanetary d-spacing calculated by using Bragg's equation are compared with standard JCPDS data. The structural properties are very close to standard JCPDS data, which confirms that synthesized nanoparticles are pure and crystalline in nature. This is introduction. Nanoparticles are very small size particles, range from 10 nm to 100 nm. Zinc oxide nanoparticle has attracted great interest of researchers due to its optical, piezoelectric, magnetic, and gas sensing property. It is frequently used in manufacture of sunscreen, ceramic-based water treatment, and as fungicide. Green synthesized zinc oxide
நீ
nanoparticle are
ப்ரெசென்ட்
free
பண்ணலான்ட்டு
from
அவங்க வந்து கூப்பிட்டாங்க.
additional
அதுதான் வெயிட்
impurity.
பண்ணிருந்தேன். ஷேர்
Plant
பண்ணா
parts
ஷேர்
are
பண்ணவே முடியல என்னோடது. அது கிளிக் பண்ணி
used for
அந்த ப்ரெசென்ட் நவுன்னு
nanoparticle
கிளிக் பண்ணி
synthesized because
அந்த
their
ஏரோ பட்டன் தானே
extract
கிளிக் பண்ணோம்.
is rich in
டேபும்
phytochemicals,
ஓப்பன்லேயே தான் இருக்கு. ப்ளஸ் இது பிபிடியும்
which
ஓப்பன்லேயே
acts
தான்
as
இருக்கு.
reducing
அந்த
and
இதில் போய் விண்டோ
stabilizing
கொடுத்து
agent for
ஓப்பன் பண்ணா என்னோடது அந்த இது காமிக்கவே மாட்டேங்குதுடா.
Wavelet Transform is a new
Okay, you can
favorable set
continue
of
next
tool
one,
and
sir. I
technique
will try to
widely used
அப்படின்னு
to
சொல்லிட்டேன்.
analyze signal and
அப்புறம்
especially
கொஞ்ச நேரம் வெயிட் பண்ணி பார்த்தேன். ட்ரை
non-stationary
ஒன்ஸ்
and
அகைன் பண்ண
transient
முடியுது.
signal.
சரி ட்ரை
The
பண்ணி
denoised
பார்க்கலாம்.
XRD pattern of zinc
தேங்க்ஸ்
oxide
சார் சொல்லிட்டு
nanoparticle
யூ கேன் கண்டினியூ
provides signal and peak
ட்ரை
with more
அப்படின்னு
clarity.
சொல்லிட்டேன். இப்போ நெக்ஸ்ட் போயிட்டு இருக்கிறாங்க. நானும் போட்டு போட்டு பார்க்குறேன். அது
This
வரவே
literature
மாட்டேங்குது.
survey, a lot of work has been done to synthesize zinc oxide nanoparticle using extract of different plants. ZNO nanoparticle may also be prepared via physical, chemical, and biological method. Chemical method may involve hazardous chemicals, high energy consumption, and need high pressure or temperature condition in process. Nonetheless, these techniques required a high amount of energy, costly equipment, so that cost of product is increased. Another approach to obtain ZNO nanoparticle is using green synthesis, which has developed as alternative eco-friendly process. This is material and method. Gel of aloe vera leaves was extracted using stainless steel knife and filtered for removing impurity. Gel was stirred vigorously at room temperature for getting homogeneous gel. A solution of 0.1 molarity is prepared using distilled water and zinc nitrate hexahydrate. Aloe vera gel 25 ml is added slowly to prepare solution 200 ml under vigorous stirring at room temperature. The color of solution was milky at initially. The solution was stirred continuously at 75-degree temperature until color of solution changed. This was a first indication of formation of nanoparticles. It was a visual confirmation of nanoparticles. The prepared nanoparticle in gel form were calcined at 400 degrees Celsius in hot air oven for 1 hour. The sample was crushed for 15 minutes using mortar and pestle for getting fine powder form of prepared nanoparticle. The XRD pattern of as prepared sample is obtained and denoised by Wavelet Transform. The signal denoise is implemented by software TrideWave with help of denoised XRD pattern. Structural property of green synthesized zinc oxide nanoparticle are determined and discussed. This is result and discussion. The XRD pattern of prepared zinc oxide nanoparticle using X-ray wavelength 1.5 angstrom is shown in figure. The sharpness of peak indicate that obtained sample is crystallite in form. The denoised XRD is obtained using Haar wavelet transform level 1. Interplanar d-spacing are calculated by using Bragg's equation 2d sin theta is equal to n lambda, where n is a order of diffraction, lambda is a wavelength of X-ray, and d is interplanar d-spacing between given plane HKL. The interplanar d-spacing and full wave at half maxima value obtained from XRD synthesized ZNO nanoparticle at shown in table 1. The diffraction peak corresponding to this plane obtained from XRD data are compatible with JCPDS, which indicate hexagonal brutalized face of ZNO nanoparticle. In Jadeno-Vrutrise structure, oxygen atoms are joined with zinc atoms such that they form a hexagonal closed pack type structure. The structural property of green synthesized zinc oxide nanoparticle show strong agreement with standard JCPDS data. This is conclusion. Green route to obtain Jadeno nanoparticle is an eco-friendly, cost-effective, and simple approach. Jadeno nanoparticle are synthesized using aloe vera gel as capping agent. The sharp peak confirms the crystallite nature of sample. The XRD pattern is denoted using Wavelet Transform level 1. The interplanar D-spacing and full wave at half maximum value are determined. The structural property of Jadeno nanoparticles shows a strong agreement with standard JCPDS data. The structural study of prepared Jadeno nanoparticle proves its pure and crystallite in form. These are pattern of XRD and denoid pattern of XRD, and this is a table for interplanar D-spacing and FWHM. Thank you, sir.
Thank you. Thank you so much, Professor. Any questions from audience side? Please raise your questions, Professor.
Yeah, Mr. Divakar.
Yes, sir.
Where have you used this wavelet transform in your this paper in this research?
जी सर, ये जो XRD पैटर्न है इसको डिनोइस करने के लिए यूज किया है सर.
So did you use any built-in softwares or you create your own wavelet transform for this particular problem?
नहीं सॉफ्टवेयर है ड्रेड वेव नाम से.
But you have not mentioned any softwares in your research paper. Why it is so?
नहीं ड्रेड वेव सॉफ्टवेयर बोला ना सर.
Okay.
इसमें है.
Okay.
ओके सर.
Thank you.
थैंक यू सर.
Okay, okay, Professor. Thank you for your nice presentation.
Thank you, sir.
Thank you. So the process, Sushil Kumar Chaudhary, R.S. Jaden, and Padam Singh, you are here means please share your presentation now. You start your presentation.
Actually, Padam Singh sir is left.
Fine. Already he presented one
and the remaining I think paper ID 44. Samara Salvi.
Yes. I may call her on.
Yes.
Yes.
Yes, sir. I am here, sir.
You start your presentation now.
Yeah. Okay, sir. Now visible, sir?
Yes, madam. It's visible.
Okay, sir. Thank you. Good morning to everyone. Myself, Tamra Chelvi, PhD Research Scholars under the guidance of Dr. G. Rajashekharan from Vellore Institute of Technology, Tamil Nadu. I am going to present my work on C exponential mean labeling of graph based on graph operations. Let me start with the definition of exponential mean labeling. A function f is called a C exponential mean labeling of graph with the p vertices and a q edges. Then vertices defined by 1 to etc q plus 1 and edges defined by 2 to etc q plus 1. These are the formula of exponential mean labeling. Next, in this paper, it is tried to analyze that some graph operation preserves the C exponential meanness property. We have discussed the C exponential meanness of graph in terms of path graph, then twin graph, corona product of path attached star graph for m less than or equal to 3, n less than or equal to 3. The total graph of path T of Pn, p square of n of graph, the middle graph of path m of Pn, Pb of A, then again corona product of path attached K2, then subdivision of S3 graph, finally MCN graph. Coming to my result, for the above mentioned graph, we have analyzed the C exponential meanness. Based on the observation, we have proposed a number of theorems along with the proofs. First, we discussed nth terms of path graph denoted as C exponential mean graph for 1 less than or equal to xi less than or equal to 3 for I equal to 1 to n. After we labeled for the standard graph, first of all, I followed C exponential meanness property labeling. Based on that, I have defined the function. After we labeled, we defined vectors function 1 to etc summation I equal to 1 to n xi plus n. Same the vectors function 2 to etc summation I equal to 1 to n xi plus n. Similarly to this problem, triangular graph of path n is a C exponential graph for n greater than or equal to 2. After we labeled the graph, we defined the vectors function 1 to etc 4 n minus 1. Then edges function is edge function is 2 to etc 4 into n minus. As mentioned earlier, P2 of P square of n is a C exponential mean graph for n greater than or equal to 3. First, we labeled C exponential mean as property of assign the labeling. After we define the vectors function 1 to etc 2 into n minus 1 and edge function 2 to etc 2 into n minus 1. As mentioned early, middle graph of path M of Pn is a C exponential mean graph. Middle graph mean if u1, u2, etc. up and x1, x2, etc. xp denoted the point and line of p, q graphs of G respectively. We define the middle graph of G denoted by M of G as the intersection of graph. Ohm of F on V of G where F equal to V dash of G union of X of G is the middle graph. First we label the graph. After we define the function, vectors function 1 to etc 3n minus 3, same to the vectors function 2 to etc 3n minus 3. Then graph PBA of PB of A is a C exponential mean graph for B less than or equal to 3. We found two cases, B equal to 3, B equal to 2 and B equal to 3. First we found B equal to 2 is a vertex function is 1, 2, 3, etc. A minus 1, A plus 2 plus 1. Same to the edges function, but starting to 2, 2, etc. A minus 1, A plus 2 plus 1. Similarly to the B equal when B is considered 2, B is considered 3, we define the function vectors function 1 to etc 3a minus 1 into a plus 2 divided by 2 plus 1. Same to the vectors function. Then Carnot product of path attached K2 is a C exponential mean graph for n greater than or equal to. Mean Carnot product mean a new product on two graphs G1 and G2 is called a Carnot product denoted by G1 Carnot product K2. The object is to construct a new and simple operation to it on two graph Q1 and Q2 is called the Carnot product. After we labeled the graph, we found vertex function 1 to etc for n similar to the edges function, but starting to 2 to etc for n. Then subdivision of S3 is a exponential mean graph. Mean by subdivision, a graph which can be formed from a given graph G by breaking up each edge into exactly two segments by intersecting intermediate vertex between its two ends is called the subdivision of graph. It is denoted by S of G. After we labeled the vertex functions, we found vertex functions 1 to etc p1 plus p2 plus p3 plus 4. Then edge function 2 to etc p1 plus p2 plus p3 plus 4. Then p of 1 to etc n minus 1 is this exponential mean graph. Similar to the function, we found it. Finally, MCN is a C exponential mean graph for n for any m greater than or equal to 1 and m equal to 3, 4. After we labeled, we found two cases m equal to 4 and n equal to 4 and n equal to 3. First, we defined two cases in subcases in n equal to 4, case 1. It's a m is odd mean, m greater than or equal to 3, then m is even, m greater than or equal to 4. We found the vertex function 1 to etc 8m, same similar to the edge function 1 2 to etc 8m. Then second case n equal to 3, we defined vertex function 1 to etc 6m. Hence f is a exponential mean labeling of mcen. Thus the graph mcen is this c exponential mean labeling for any m greater than or equal to 1 and n equal to 3 comma 4. Conclusion: in this paper, the C exponential mean labeling of graph was introduced and discussed its meanness of some standard graphs based on graph operations. This preliminary observation of simple graph can be adapted to label the complicated graphs. This mathematical finding can be implemented to design electrical and digital circuit in the field of electronics and wireless network. These are the references of my paperwork. Thank you to all.
Thank you, Professor Thamalisuri, for your nice
Yeah.
presentation.
Okay.
Any questions from audience science? Please raise your questions, Professor. I think there is no questions. Thank you, madam. Thank you.
Thank you, sir. Thank you so much, sir.
Okay.
Professor, I think all the presentations are over.
Yes.
Shall we conclude?
Yes, sir.
Yes.
Thank you so much. Thank you so much, Dr. Sanjay sir and Dr. Vijay Kumar sir, for the
Thank you.
for chair the session very nicely and within time. And
Thank you so much,
for
Professor.
thank you for the valuable comments to all the participants and presenters in this technical session. So thank you once again. And I request to all of you, please on your camera for one pictures. I request all the participants, please on your cameras. Skip. Thank you so much, all of you.
Thank you,
Thank you,
Professor.
Sanjay sir. Thank you, Sanjay sir.
Thank you.
All the participants, I request to join the invited talk at 12 noon with the given link in your schedule and WhatsApp group also. Please join. Invited talk by the Professor J. Prakash from New Zealand.